Question number 2, work is the product of force times displacement. So in this case, we're lifting. So the displacement is delta y. Now, it doesn't hurt to draw a force diagram. It really makes things a lot easier, right? So here's this force that I'm exerting upwards on some textbook, and its weight is going down. So the key here is that there's a constant speed. So if I want to figure out how much work I did, the first level, I need my force in delta y. Well, delta y is 3 meters. There's no reference to how much force that I have to exert unless we understand that at a constant speed, the sum of the forces must equal 0. So that the force I'm exerting must be equal to the weight of the object. So in this particular case, the work done is equal to the weight of the object times delta y, which we know we can calculate weight as m times g times delta y, which would be 4 kilograms times 9.8 meters per second squared times 3 meters, or someplace in the range of, I think, 117 joules. Now, just as a side note, remember, we also could have said, oh, okay, well, work is equal to the change in potential energy as I lift this thing 3 meters, which would be, again, m times g times h, or delta y, no matter how you change it. Okay, how much work did I do on the 4 kilogram textbook, question 3, if I push it 3 meters across the table? Well, again, my force diagram would lead me to say, okay, here's this textbook. I'm pushing with some force F. There's clearly friction because it references the coefficient of friction. It's got to be a friction force in the opposite direction. There's also a normal force and a weight force. How much work do I do? Well, again, work is equal to my force times delta x. Well, we've got a reference of delta x. It's 3 meters across the table. Well, how much force do I exert? Again, there's no reference to that. But what there is reference to, the fact that I'm moving this thing across the table at a constant velocity, which tells us then that the sum of the forces in the x must be 0. And that tells us that FF is equal to F. So I don't have reference to what force I'm exerting, other than the fact that I know it's numerically equal to the friction force. Well, how big is the friction force? It's mu times the normal. We've been through this. Or mu times the weight, because we know that the weight and the normal force have to be equal to each other. Or mu times m times g times delta x. And if I plugged in all those numbers, 0.2 times 4 times 9.8 times 3 meters, I'm going to get 23.52 joules. I pushed the same book across the same distance with a force of 20 newtons. Well, now for part A here, all right, part A, my work is just my force times delta x, or 20 newtons times 3 meters, or 60 newtons. What's the work friction does on the book? Well, the work friction does on the book is determined by the friction force and by the distance that it's moved. And the friction force is determined again, just like up here, by mu times the normal force. Guess what? None of that stuff has changed. Up here, if I do 23.52 joules of work and the object's moving across the table at a constant velocity, then there's no added energy, which means there's no net work done. So me and friction are both doing 23.52 joules of work up here in question 3. Now you go to question 4 and I push harder. So I do more work, 60 newtons. But nothing changes with respect to friction. So the work done by friction is still 23.52 joules. Because if I did friction force times the normal force, or I'm sorry, if I did mu times the normal force times delta x, it'd be the same values as it was up there in question number 3. Now, what's the net work? The net work is the subtraction of 60 minus 23.52. This is positive work. This is negative work. What's the net work? It's the difference between those two things, or 36.48 joules. And since our whole basis of our lesson today is that the net work is equal to the change in energy, then part D is also 36.48 joules. Now, if we go to the back, what's the new kinetic energy of a 3 kilogram object that's being pushed across a frictionless floor with a force of 6 newtons for a distance of 4 meters? Well, remember, work is equal to the change in energy. So if we assume this thing started from rest, which as I read it, I guess is a little ambiguous, then the new change in energy can be calculated by taking the force that's being exerted times delta x, which is equal to my new change in energy, which is simply 6 newtons and 4 meters. Oops, sorry, 4 meters equals my change in energy, which is 24 joules. What's the change in kinetic energy of the object? Okay, so again, question number 6, the change in kinetic energy. Well, I could do 1/2 mv squared, but there's no reference for what the velocity is. So our change in kinetic energy is going to come from the net work done. Now, our net work is going to be our net force times our delta x. Now, this is essentially doing question number 4 all in one step. So what's our force diagram here? We've got this 30 Newton force, friction's going in the other way. I've got my normal and my weight going this way. Well, what's the value of my net force? Well, that value of that net force, which will equal the change in kinetic energy, is this 30 newtons minus the force of friction times my delta x. Well, I know delta x is 3 meters. I don't know the friction force, but I could calculate it. It's mu times m times g, or mu times the normal force. So 30 newtons minus mu times m times g times delta x gives me the change in kinetic energy. Delta x is 3 meters, g is 9.8, m is 4, mu is 0.4. My change in kinetic energy becomes basically 43 joules. 42 and a lot of change. How much work is done to compress a 50 Newton per meter spring? Now remember, that's my K value. We're compressing it this distance x. How much work is done? Well, work is equal to F times delta x, but there's no reference for F here. So then the work done is equal to the change in energy, which in this case is equal to the change in elastic potential energy, which is equal to 1/2 times K times x squared. 1/2 times 50 times 0.4 squared gives us 4 joules of work done. How come? Because then there's now 4 joules of stored energy in the spring. Finally, if we get down here to question number 5, we did 8 already in class. What's the new speed of a 5 kilogram object if it starts with a speed of 9 and a force of 40 newtons is exerted in the same direction of motion? So now look at same direction of motion. That's going to cause my kinetic energy to increase because V would increase. So how much will that kinetic energy increase? That kinetic energy increase, that change in kinetic energy, will equal the net work done. I need to find here a new speed. Well, my change in kinetic energy is kinetic energy final minus kinetic energy initial. And that's going to equal my net work. Well, what's my net work? My net work is a force times delta x. Now again, we're looking for a final speed that's not even worked in here yet. How do I get it in there? 1/2 m times v final squared minus 1/2 m times v initial squared is equal to F times delta x. I am trying to find this v final. So if I know everything else, I'm good to go. Well, it's a 5 kilogram object. A 5 kilogram object starting with a speed of 9 meters per second. A force of 40 newtons is exerted on it, a direction or a distance of 6 meters to cause this speed to get bigger. That speed should be bigger than 9 because again, the force is being exerted in the same direction as motion. If I do all that algebra and I substitute all that stuff in there, the final velocity here ends up being 13.3 meters per second.